know Mr. Ryan, right?
Yeah.
Okay, so we're given an array of positive integer, we give them a target, right? Do you still remember what's the difference between the subsequence and subarray?
I
Right?
think one of them is continuous.
Yeah, one of them is continuous. Subarray is continuous, right? So 1, 2, 1, 2, 3, 2, 3, 4, continuous. Subsequence is not. So basically, subsequence is that you can remove 0 or more elements from the original array. For example, if I remove the 1, 4, 5, and the remaining is 2, 3, this is subsequent. Or if I remove 2, 4, the remaining is 1, 3, 5, so it's a subsequence. Subsequence, for each element, you can pick or skip. You can include it or you can discard it in the subsequence. So basically, subsequence includes the subarray, right? Includes the subarray. Subsequent includes the subarray. So if we draw this Venn diagram, subsequent, and then this is subarray. So usually for subarray problems, we can brute force. That's going to take O(n) squared time to brute force each pair of the subarray, right? We can actually brute force 2 index, the left and right. So another way to count the number of subarray is that one single element is a subarray, right? So there are how many possibilities of the one single element? If their size is n, so there are only n, right? If the subarray is size of 1, then there are n. So Cn1, okay? So subarray of more than one size, then it's actually Cn2, right? Because we pick one index for the left, we pick one index for the right, so it's Cn2. So this is n times n plus 1 divided by 2, and this is O(n) squared, where the O(n) squared comes from. But today we're going to talk about the subsequence. Oh, okay, so the question is that we want to find out the longest subsequence, which is the sum of the given target t. So in this case, what's the longest subsequence that adds up to 9? What's the longest subsequence that adds up to 9?
2, 3, 4.
2, 3, 4, 3, yeah? So this is the longest. Of course, we can do 4 and 5, but there's only 2 elements, right? Can we do? No, I think that's it, right? Or maybe 1, 3, 5, 3 elements. Okay, so we want to return 3 for this, the longest subsequence. So we have seen similar problems like longest subarray, right? Or longest increasing subsequence, right? We talk about this. But today it's longest subsequence. It does not have to be increasing. So if it does not have to be increasing, it means the sequence is not important, right? For example, like 2, 3, 4 is the same as 4, 3, 2, right? So in this case, it's kind of the knapsack problem. So in mathematics, we have a type of problem which is knapsack problem, right? We talked about that before, knapsack. So for this one, so we can imagine we have 5 different kind of goods, different type of goods or toys, and each one has different weight. We have 5 different toys which are different weight. So the first toy is 1 kilo, the second toy 2 kilos, and etc. It's one kind of the knapsack problem. This question is that we want to maximize the number of the knapsack. Okay. Another variant is that you're given a certain number of knapsack, and then you can put the goods in the knapsack, which each knapsack has a capacity, and then we want to maximize the number of values for each good. We have a different type of value. So there are quite a lot of variants. This is one of it.
But there's a t, so that means all the value combined must be t. So
that's right. Yes. So but this one is that we want to maximize the number of the knapsack. Yeah, so we want to maximize because it's the longest.
But if you have more, it doesn't matter because then there'll be lower value because they all.
Yeah, so this one is not the it's one variant, but it's not maximize the value. It's maximize the number of the items picked. Okay.
I think that the value thing is a very good example because they're exactly the same values, except there's more.
True. Yeah, you're right. Yeah, so each item has the same value. Yeah. Okay.
Yeah.
So
No, I mean the sum has the same. The sum is just the value of the sum.
Okay. So how do we solve this problem? So how do you know it's 2, 3, 4? Because this is a simple example, we can just look at it and then we can just guess. Okay, it's 2, 3, 4, 3 numbers, the maximum. But if it's
why not
if
3,
it's a
4,
bit
5?
3, 4, 5, because 3, 4, 5 is 11 is more than the target. Okay, so if there's a corner case, right? If we can't make such arrangement, so if we can't pick any items here, so let's add up to exactly t, then we return -1, right? For example, like 1, 2, 3, and if we want to get the 10, obviously this is impossible, so we return -1. As I said, for the subarray, right, we can brute force this O(n square, we can brute force we can iterate the left index, the right index, and then this is a subarray. But for the subsequence problem, so for each item, how many choices can we have? How many choices do we have for each item? Suppose that we are looking at this item 1. So how many choices do we have? Two, yes. What are those two?
Pick or not pick it.
Yeah, pick or skip. Okay, we pick or skip. We can use the f function, right, for the index I if we are picking from the left to the right.
Does it have to be consecutive numbers?
Consecutive.
Three numbers in a row?
No, it doesn't have. This is the subsequent. Okay, so this is the index, and then this is the remaining sum, right? This function returns the longest subsequence if we start picking from the ith item, and then we have the remaining sum to pick. Okay, so we have two choices, right? But we have to write, this is the recursion function, remember? We have to write the base cases, which is once we reach the right boundary, so we need to check, right? If I equals the length of A, we have to check this as remaining sum, right? If remaining sum, it returns 0 if the sum is 0, otherwise we return -1, not -1, minus infinity here. Okay, why? Because we want to maximize. So that's why we want to give it the smallest number we can think of, which is the minus infinity. Okay, minus infinity. Yeah, infinity is like that, right? Infinity minus infinity. Any point, if s is smaller than 0, then we also need to return minus infinity, right? So if the sum becomes negative, it means that we currently have too much item, which is more than the capacity t. Am I right? So okay. So now we have two choices. If we pick, then we have fi plus 1, and then s minus ai, right? This is to pick. This is current sum to pick this item. If we want to skip, how do we skip? If we want to skip, so it's f. We start picking from we skip the current item, which is I. So what should I put here? Skip. If we skip, this is the sum. S, just S, right? Because if we skip, then the sum doesn't change. Alright? If we pick, then we need to deduct this item from the sum, right? But look, we want to plus 1 here, right? But this one could be minus infinity. So we come plus 1 to the minus infinity. So we have to check, right? So if
Why
P...
plus 1? You just like, we need to plus 1 and then like, blah, 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 blah.
Okay, we can't add 1, okay? We can't add 1. If P is not equal...
Why do you need to add 1?
Sorry?
Why do you need to add 1?
Good question. Why do we need to add 1? Yeah. Look. We already pick. If we pick it, so the length should be increment 1, right? This is the point. We pick it, so we pick one number, so the length.
That fi plus 1, that stuff is like, what's gonna happen?
Look, we are picking from the index I.
Yeah, but then
This is I.
Then you like add 1.
Okay.
But it seems like you add 1 to that instructions.
I see. Okay.
And then it doesn't say the length there.
That's right. Okay, let me explain it one more time. This function, f function, returns the length. Okay, the answer, the length of the longest subsequence. If we start picking, from the ith item to the right? So for example, ith item, and we have remaining sum. So at the beginning, we need to call f0 and the target, right? Because we want to start picking from the first item, and we have remaining target to pick. Okay, so why we need to plus 1 here? Because we are already picked this item, right? This is the choice. We pick this item, so we need to add 1 here because we already pick one number here, pick one item here. Okay, if p not equals infinity, then ideally we just plus 1 here, right? The thing is the minus infinity come plus 1, right? Infinity is not a number, right? Ryan, you said it last time. Infinity minus infinity, this is not a number, this is just a concept. You can't actually add 1 to the infinity. It makes no sense, right?
But
okay.
Infinity plus 1 is infinity.
Infinity subtract infinity is 0, right?
Infinity,
no, okay.
Infinity, you can't subtract infinity or
No,
do any
okay.
You can't do an operation.
They're the same thing.
Mathematics, you have to be precise and accurate. You can't just say, okay, infinity minus infinity is nothing. No, it doesn't work that way. For example, like 0.999, yeah? It goes infinity, right? Okay, so this actually
It's basically close to 1.
is actually 1. Infinity, this is actually 1. I can prove it, but I show you it's not precise proof, but it's actually 1. Why? Look, if this, I said that x equals this, right? 10 times x equals 9.999, okay? If we subtract 10x minus x equals 9x equals this one, subtract that.
But you said that.
Equals 9, then x equals 1, right?
Yeah, but you said that. Oh, you can't subtract.
That's right. The problem is that you can't subtract infinity with the infinity. So that
because if the first one has infinity
Yeah.
lines, then the second one must have infinity and infinity subtract 1, but you can't do that after the decimal.
no, the thing. Yeah, you're right. So this is not rigorous, a very strict proof, right? You can't say okay, times x, then you just move this point 1 position to the right, and you can subtract these, and then infinity subtract infinity. You basically say infinity subtract infinity equals nothing, right? Yeah, you are saying.
No. But but if the top one after the decimal place has infinity 9s, then the 10x must have
Infinity plus 1, right?
No, subtract.
Oh, subtract 1. Yes, you're right. Okay. Yeah, okay. Yeah, this is not precise. Okay, this is not precise. But you can research and then you can tell me why 0.9999 is actually 1. You can tell me to prove in other way. Okay.
Very close.
Very close, but actually it's equal. Okay, so the conclusion is right. The proof is not right. Okay. That's the thing what I'm talking about. Okay, so here if it's not infinity, then we need to plus equal 1, and then we need to return the maximum of 2 choice, which is to pick and to skip, right? Calling this function answer, we need to call this function answer equals f0. We want to pick from the first item, and then we have remaining sum to pick, and then if this answer equals minus infinity, then we return minus 1. Otherwise, we return answer. Okay. One thing missing.
Cache.
Yes, cache, the memoization part, right? We need to memorize it, otherwise the time limit will be exponential. So because this is a search tree, right? FIS, then in each one you have 2 choice. Basically, you basically have 2 choice. This is to pick, this is to skip, and for each one you further expand into 2 choice. This is basically by the tree, and then some nodes will be calculated over and over again. So we need to cache it, right? This makes it a top-down dynamic programming. Okay, but the time complexity and space complexity is O, the length of A times the T which is the target, and this could be still very huge. The length times T. Basically, there are 2 parameters, and we are caching it. So we are caching it. How do we analyze the time and space complexity? For every combination of the first parameter and the second parameter, we are caching the states. For each I and S, for each combination of I and S, we only calculate it once because we are minimizing the value. It will be calculated only once. Okay, so that's the time and space complexity. Okay, so of course this is top down, right? So next lesson we'll talk about how to implement it using the bottom up, right? We talked about this before, right? Bottom up without the recursion. We're using the array, 2-dimensional array to store the values. The top down and the bottom up, right? Look, this is the search tree for I, S, and for each one it has expanded into 2 search tree, right? Okay, so for example, if you want to calculate this value, you recursively call these 2 functions, recursively call this until we know this base case, and then once we have these values in the leaf nodes, we come back to solve a parent node until we get this value. This is top down. We're using the cache. So, for example, if this value, sometimes this value is the same as this value. If we calculate this here, we need to save it. We need to minimize it. So when we want to calculate this value, we see, we look it up in the notebook. We say, okay, we have calculated this value before, so we don't need to expand this tree again because we already calculated 5 minutes ago. Then we just look it up. So
5
this
minutes.
this is example. Okay.
The computers can solve in like 2 seconds.
Yeah, it could be. This is example. Okay, so the bottom up is just working out from the base value and then this way, right? This is bottom up. Okay. Top down, bottom up. Okay. So what have you learned today?
We learned about knapsack.
Knapsack.
There's no point of getting knapsacks.
No, that was an example.
That was example. Okay. So we want to find out the longest subsequence,
Just
right?
like he was talking about bird holes.
Okay. So Eric, can you give me a quick introduction? Yeah.
We have an array and then we're choosing
Which is yeah.
the most amount of numbers that equal
The tabby, right?
t.
So basically, can you explain the idea? How do we solve this problem?
We use our brain.
Top down.
Top down dynamic programming,
We
right?
go top and then
So
down.
for each one, we have how many choices we have? For
2.
2, yeah. Pick or skip, okay? So for example, this one, right? We can solve the array. It doesn't matter, right? So subsequence. If we solve this array, it doesn't matter. If we multiply up the sequence, it doesn't matter, right? Doesn't matter. It doesn't matter, right? Yeah. We pick 2, 3, 4. It's the same as 2, 4, 3 or 4, 3, 2. Am I right? Yeah. So it means we can multiply it up. So to speed up, we can solve this array in the descending order. So for example, we can start picking the larger number, the larger item, right? That will speed up. Okay. Why? Because if we pick the t, the bigger number, this t, the second parameter will be reduced quicker. Am I right? The second parameter will be reduced quicker, so it will be faster. Okay. So that's it for today. Bye bye.
You spat on me. Bye.